All right, so welcome to the third video in week 2. So the topic today is fundamentals of experimental design, and in this particular section I want to talk about the importance of choosing a baseline. So one of the things I talked about in the very beginning of this class was that bold is a relative measure. I'm interested in the activation in some condition relative to another condition because the numbers that are actually produced by themselves are meaningless. And in fact, if you go into a scanner today and your whole brain average is something like 700, you could go back in 15 minutes later or tomorrow and get an average of 12. So the number doesn't matter. It's how those numbers compare within a run. Those are the relative changes that we're interested in, which means that we always need to be comparing what we're interested in, our task, to something. And that something is normally referred to as a baseline. So typically, the goal is to identify some sort of neural correlates for process of interest. So you have an activation task that's causing you to do something that you're interested in, and you're going to compare that to a baseline task that doesn't have the person doing that thing, right? And the way you do this is just by a simple subtraction. You take the activation task, you subtract out the baseline, and the difference should include your process of interest. That's the basic subtraction logic that's used in a lot of fMRI. So the traditional example is the one that I talked about from the beginning with Peter Bandettini with this hand motor area, right? So the idea here is that you're doing a sort of a tapping that involves clearly the motor aspect of moving my hand and therefore includes primary motor cortex. And then when I'm not doing anything, there's no primary motor cortex involved. So the activation task is finger tapping. My baseline task is rest, where I'm not finger tapping. And I identify parts of the brain that are sensitive to controlling my hand. And you can see here in this particular example, you can see activation here in what's called the hand knob of primary motor cortex, which is very much what you'd expect, but it's not limited to that, right? You also see this activation here in the supplemental motor area, which is probably post hoc related to the fact that I'm trying to keep the task demands in memory and the motor task that I'm doing and then I'm not doing and then I'm doing. So it's not simply the case that I've come up with an activation and a baseline whose difference is unique to, for instance, finger movements. That's a problem. And in fact, we normally refer to this as the assumption of pure insertion, right? So I may have naively assumed that moving my fingers versus not moving my fingers, the only difference between them was the thing that I'm really interested in, which is finger movement, right? And even the way I've said it, that's sort of a plausible kind of story. But that's just almost never the case. I mean, it's very, very rare that you can design an experiment like that. Instead, what happens is that you design the difference, and that difference exists, but it's not by itself, right? There are other things that are there. So there's a memory component when I'm moving my fingers. There's a sensory component in the sense that I can get sensation from the fact that I'm touching my fingers, which I don't get here. And all of those differences mean that the activation task and the baseline task are more different than just the process of interest, right? So you have to be very careful about assuming that whatever it is that you're really interested in is the only difference between activation and baseline. And this assumption is known as the assumption of pure insertion. There are normally two ways to look at baselines. One is to try to make this kind of pure insertion argument as best possible, and that is to make sure that the activation task and the baseline task are as close together as possible. The thing that they really differ in is the thing that you really care about. Otherwise, you try to minimize all the other restrictions. There's a very different way of looking at things, which is to say, actually, there are going to be a lot of differences between my activation task that definitely includes the process that I'm interested in, and my baseline that definitely doesn't. And the more differences there are between them, the more of a large physiological effect there's that much of a difference, it makes it easier to detect. So my statistical sensitivity is going to be improved by maximizing the distance between my activation task and my baseline, okay? And by doing that, you increase the effect sizes, which makes it easier to detect a difference. The downside of that is it tends to identify systems rather than specific regions. If the two tasks, the activation and the baseline, are quite far apart, then yes, there will be something related to your process of interest in all likelihood, but there are all sorts of other aspects. And you could see that in the hand tapping example. You could identify part of the motor system, but it wasn't specific to, say, primary motor cortex around the hand. One of the most common low-level baselines that people use is just rest. So that is, they pick something where somebody's just told to relax for 30 seconds or something when they're not doing the task. And there are good and bad parts of rest. I mean, it's very, very easy, and it is quite a low-level baseline, but there are things about rest that are potentially problematic, and it may depend, they may be more problematic for certain kind of paradigms than others. So for instance, during rest, a very common phenomenon is internal speech. You might be sitting there in the scanner sort of saying, geez, this seems like a long time, or I'm really bored with this, or I'd like to get up and get out, and I need to do the laundry. All those kind of things are very uncontrolled, right? And you may be doing that, I might be doing something different, but all that time there's some kind of inner monologue that may be happening. And for instance, if you're comparing that to sort of an explicit language task, the difference may be less than you expect, simply because there's language happening in both cases, it's just uncontrolled in one form. The other thing is there are these resting state networks. So I talked about this a little bit in week 1 when I talked about some of Biswall's work, and said that he was able to identify the motor system even while people were at rest in terms of correlated activity over time. So the whole field of resting state networks has increased dramatically over the years, and there's been some fantastic work. This is particularly one of my favorites. It's from Christian Beckman, who was at Oxford at the time he did it. And he used a more sophisticated kind of approach. He used an independent component analysis approach to look for consistent structured networks in people who are lying at rest in a scanner, told to do nothing. And what you can find is that there are sort of anatomically and functionally meaningful things here. So for instance, if you look at the A part of the this slide, this is activity in sort of primary visual cortex, right? Whereas if you start looking at the B component, well, this is extrastriate visual cortex, including posterior parietal regions that are often associated with it. If you look at C, these are networks that are in and around Heschel's gyrus, which is primary auditory cortex. So this is primary secondary auditory cortex, and the kind of thing that you would get very robustly if you were, for instance, listening to someone speak. And it goes on and on. D is this primary motor cortex activation that we saw with Biswall, etc. So at some level, me putting labels on these is not entirely a sensible thing to do, right? I mean, I'm basically reading tea leaves when I do that. But it is striking when you look at them that they very much match the kind of patterns that you see in certain types of paradigms. So they don't seem to be meaningless and completely insensible. Quite the contrary. They seem like they have sensible sort of structure that we see time and time again across lots of different experiments. And moreover, you can see these across individuals. So the fact is, we're not talking about idiosyncratic things in one person. We're looking at structured noise in resting states. And of course, if you're comparing your task that's activating one of these areas to some sort of system of structured noise, again, you might minimize the difference between them by simply choosing an unconstrained baseline that isn't giving you exactly what you expect. So the alternative are these kind of high-level baselines, and that is where you want to minimize the difference between the activation and the baseline conditions and try to restrict it specifically to the process of interest, right? And the way you do this is you can either do a task change or you can do a stimulus change, but not both, okay? And I'll take you through the logic of that. In addition, what we have to worry about are sort of implicit processing that you may not specifically be thinking about, because sometimes where it's very clear that there should be a difference according to some, for instance, psychological model, that doesn't necessarily mean the brain knows about your psych model and follows it. Okay, so a task change is when the stimuli are kept the same, but the task that people are doing with them varies from one condition to another. So in this experiment that I ran, my goodness, years and years ago at this point, people see words on a screen and they have to either focus on what the words mean, so they did a semantic task. So for instance, they had to decide, is that a man-made item or not, and press a button, yes or no. Or they had to focus on the sound of the word. Does it have 2 syllables or not, and press a button, yes or no. So the word itself is exactly the same, but the way the person processes the word changes, right? So the difference here is whether you focus on meaning or you focus on sound. And you can see from the activation patterns that there are different parts of the brain, particularly areas in the frontal lobe and in parts of the parietal lobe, that are very, very sensitive to whether or not you're focusing on sound or you're focusing on meaning. And that becomes important because the difference between them is very, very minimal, right? All you've done, you've kept the stimulus exactly the same, but all you've done is changed the type of processing, and that's the thing that you're interested in. So that's an example of a high-level baseline. Another high-level baseline would be to keep the task the same, but change the nature of the stimuli. So this is an experiment that Charvi Narain ran years ago, where she had people listening to intelligible speech. She cut with a knife versus listening to unintelligible speech. Right, I can't make those noises. But in both cases, the task is the same. They're listening and trying to figure out what's being said. It's just that different types of things are being used as stimuli, intelligible versus non-intelligible. And again, because the task didn't change, the only thing that changed is the stimulus. You can directly compare them and see that there are parts of, for instance, the superior temporal sulcus that are very sensitive to whether or not the acoustic information carries meaning or doesn't carry meaning. And that's a very, very good design. I've said before that you can't change the task and the stimulus because then you can't determine what's going on. And let me just give you an old example from the late 90s from Mark Desposito's group, where they were interested in trying to identify where in the brain visual imagery existed. And they had a task where they would give people words and say, generate a mental image. So I'd see the word banana, and then I'd have to visualize in my head what a banana looked like. And then their baseline was listen to these words that are about abstract items. So you'd hear the word government, society, whatever. So in this case, there are two things that are changing. Not only are you moving from concrete words to abstract words, so the stimuli are changing, but also the task is changing. In one case, you're visualizing a concrete word, and in one case, you're passively listening to an abstract word. So there are all sorts of things that are going on in the brain here, but there's no way you can uniquely tie them to visual imagery, because maybe it's due to the task change, maybe it's due to the stimulus change, maybe it's due to some interaction between them. This design doesn't allow you to draw that kind of an inference. So it's really important that when you're trying to design a high-level baseline, you either change the task or you change the stimulus, but you don't change both. And I also mentioned that there are cases where you can come up with really, really clever designs. It doesn't necessarily mean the brain's going to play along. So this is a study that Kathy Price did years ago where she asked people to read words sort of incidentally. So there are words on the screen like captain, and then there are words, non-words on the screen like Plutarch or something, right? Something that's not a word in English. And if you, at a theoretical level, you might think, well, look, in one case there's meaning, in one case there isn't. Comparing words to pseudo-words should still give you where in the brain meaning is, because they both have sound, they both have written forms, they have all those other things, but where they differ is one has meaning and one doesn't. And of course, there's a ton of psycholinguistic theories that suggest that that's exactly correct. However, that's not at all what you see in the activation in the brain. What you see is that your brain activates the same parts of the system to identify words as it does pseudo-words. And one possible explanation for that, which seems to be certainly very plausible, is that your brain doesn't sort of have a dictionary that it's sort of looking at. It sees the word and then tries to add meaning to it. So it's still trying to add meaning, even if it's not a word. It's just working harder and probably failing relative to when it actually is a word and it knows what the meaning is. But in both cases, it did sound processing, it did meaning processing, and it didn't respect the sort of clever little psycholinguistic theory that's different between them. And Kathy's group was one of the ones that showed that, it's really important that when we're trying to relate our cognitive models, that we don't get too hidebound by these assumptions that our models are right and then we should just find them in the brain. Because sometimes the brain tells us that in fact our models are wrong and gives us new information about how we need to design our models. And that's actually a super valuable contribution from something like fMRI or even positron emission tomography. Okay, so if we just summarize what's going on in baseline here, choosing an appropriate baseline is as important as choosing your activation task, because what you're doing is always looking for these relative changes. You're looking for the difference between what's happening in your activation task relative to the baseline. If you just don't pay any attention to the baseline, then you have no idea what the relative changes are and what they mean. You have to take the baseline very, very seriously. The two big problems with baselines are the assumptions of pure insertion. This idea that the only difference between your activation task and your baseline is the one thing that you're interested in, because that's just often not the case. Or this issue of implicit processing, where there's, you have this cognitive model that has a very clear difference in it, but that isn't respected by the brain. Your brain is doing something that's different than the sort of model that we talk about in psychology. And as a result, the activation patterns that you see don't fit the design at all. And in fact, in some cases, you would see no difference whatsoever and have a complete null result in your fMRI, which would be a very sort of gruesome waste of time and resources. One of the things I always recommend for people is that multiple baselines can be a good thing, right? So if you have a good sort of high-level baseline, it's often very sensible to include a low-level baseline as well. And the reason for that is, in case your high-level baseline assumptions are wrong and there are no detectable differences between your activation and your baseline, if that's all you have, you got nothing, right? You have literally no results and you've wasted everybody's time and efforts. On the other hand, if you included a low-level baseline as well, then you can look at both of them relative to the low-level baseline and determine, did the experiment just not work? Or did these two tasks that I thought were different actually give the same pattern of activation, which I can see because I can see it relative to the low-level baseline. So I'm a very big fan of including multiple baselines in an experiment so that any assumptions that we make about the high-level baseline that turn out to be false don't mean that we've lost the entire data from that experiment.